Welcome to calculus. So we're going to be looking at what we can do with different types of integration processes. Namely, what we're going to look at here is what we can do when we get something that's a little bit more complicated looking than this piece right here. It doesn't necessarily mean that the problem itself is harder. It just means that we need to deploy additional pieces to this. Now, this one in particular, we talked about this in a previous video, that we just simply rewrite this as x to the negative 3 dx. You add 1 to the exponent, and you get x to the negative 2, divided by that new exponent of negative 2, and then you get plus c on the end of that. All right, so now that's pretty straightforward. That's not really a problem. But what if we change things up and we say we're doing the integration of ln of x to, say, the 8th power, and we're putting that over x, and then we have our dx on the back of this. Remember, the dx is our adverb. It's telling us what we're integrating, what variable we're going to integrate. And if you want a little bit more explanation on that, I'll do an example here in another video probably. That kind of reiterates the idea of why we need this dx here. Okay, so what do we do with this? Now, we can't just do this integration like we did directly above this, because if we add 1 to the exponent and divide by that new exponent, we have these other pieces that we're not accounting for. We have the ln of x that we're not accounting for. We have division by x we're not accounting for. Furthermore, this right here, ln of x to the 8th power, with the way we have this written, is not a power function. So we can't just deploy our power rule for integration to do this. So what do we do? Now, this is where integration by substitution comes in. Okay, so what we're going to do is I'm going to pick u, and I'm going to let u equal ln of x. Okay, now I'm going to then I'm going to find that derivative, and that derivative would be 1 over x dx. Now, a couple pieces I want to explain with what's going on here. First and foremost, I can do anything I want to an equation. If I want to keep it balanced, I have to do the same thing to both sides. So I can take the derivative of the left and take the derivative of the right, and I've maintained the equality. All right, so I do du. I did the derivative of u, which gives me the du. I drew the derivative of x, which gives me the dx. I account for the change for both of those pieces. Derivative of ln of anything is 1 over that thing times the derivative of its interior, which is where that dx comes from. So there we go. So there's those two pieces. Now, why is that useful to us? Well, for one very important reason. I'm going to grab my highlighter here. So this right here, ln of x, is right there. Okay, let me change to a different color here to kind of color code these things. And here is 1 over x, and you're like, well, I don't have 1 over x over here. Well, I have the dx, which is right there, and then I have 1 over x. And you kind of have to look at that a little differently. So let me just try to rewrite that so it makes it a little bit clearer of what we're dealing with. We got 1 over x times ln x quantity to the 8th power, and then dx on the end of that. Now you can see we have 1 over x dx, okay? This little piece right here, and this little piece right there, right? And we have its separate piece, which was the ln of x. Now, what that does for us is it allows us to be able to rewrite this. I'm not using an equal sign because I'm changing my variables here and changing the way this looks, so it's not exactly the same function, but it's going to have the same behavior. So then I'm going to say, well, I can replace 1 over x dx with du because they're equivalent right there. I can replace ln of x with u, so I got u to the 8th power. Now I can integrate that a lot easier. So that gives me u to the 9th power divided by 9 plus c. All right, so that's what I can now use the power rule for the power function, and I get this. Now the thing is, I'm still not in the original, using the original variables here, so I got to switch back to my original variable. So ln of x quantity to the 9th power over 9, and then plus c. Now, if you remember your chain rule from when we were doing integrations, you'll remember that when you do this process, the chain rule will tell us that we do the derivative of this thing, which would be 9 of stuff to the 8th power divided by 9. The 9s would cancel away. That'd give you that piece. And then you do the derivative of ln of x, which would be 1 over x. So that derivative, if you want to kind of prove this to yourself, I'll write this derivative out in longhand. That derivative is going to be 9 ln of x to the 8th power over 9 times 1 over x, because the derivative of ln of x is 1 over x. The derivative of something to the 9th power is 9 times that thing to the 8th power. And it was already over 9, so the 9's cancel, and then you end up with what we started with over here. Okay, so that completely takes care of this. Now this is called integration by substitution, and let's work a couple more examples here, if we will. So let's just say, we want to do the integration of, let's do something a little bit more complicated, huh? People are afraid of trig. Let's do a trig problem. So cosine to the 5th power times sine of x, and then don't forget our dx there, right? Okay, so now what do we do with this? Now, I'm hoping that you're not legitimately scared of trig functions, but let's just kind of play around with this a little bit. Now the problem we have here with this one is that we have two different trig functions and we have a power in there, so what do we do? Well, what I'm going to do is I'm going to kind of look at this in a different way. Now some of you are thinking what this fifth means. This fifth means that they're taking cosine of x to the 5th power, so you could actually put parentheses around that cosine and put the 5 on the outside. Well, the fact that the cosine is inside of a power like that, that's an indicator to me that that's the piece I want to pick for my u. So cosine of x. And then we know du, if we use that same thing we did up there for the other one, that same rule tells us that we'd want this to be negative sine of x. And don't forget your dx. Now, if you notice, now I have all those pieces. I have the cosine of x, which is right there. So now I'm going to have u to the 5th power. And I also have sine of dx right there, sine of x dx. Okay, so I have those two pieces. Now the thing is I have this extra negative sign here. So I just need to account for that when I rewrite this. So now I have u to the 5th power dx, and then I have to account for the negative sign, so I'm just going to put it right there. Because one of the other things I could do here is I could just divide both sides or multiply both sides by -1, right? And then the negatives would cancel on the right, and I have sine x dx equals negative du. So I'm just going to stick that over there. Now I can do that integration. That integration would give me negative u to the 6th power over 6 plus c. And then I'm going to rewrite that back into my original variable. So it gives me negative cosine x to the 6 over 6 plus c. We don't normally write it that way with the parentheses with the trig functions. Normally we write it like this. So negative cosine 6 to the 6 x over 6 and then plus c on the outside. That's how we normally write that. But all that means is cosine to the 6th power over 6. Those are the same statement, and one's not really wrong. Just this is standard notation on this second one down here. All right. Now, what else can we do with this? When it comes to dealing with substitution gets us out of a lot of really interesting situations. So let's just kind of look at another example here. Okay. So let me do this one. Let's say we want to do the integration of cosine. That's not a very good S, is it? So cosine of 1 over x, and then x here, and then dx. Okay? Oh, squared. Otherwise, it's going to get a little messy. All right, so what do we do with this one? Again, when we're looking for substitution, what we're really looking for to a large degree is reversing the chain rule. Okay, that's ultimately one of the things we're trying to do here. So what we want to do is look for how we can do a substitution where we're taking one piece out of a known function. And when I'm looking at this, and there's lots of different ways you could try to do this one, and I'm just going straight to the easiest spot here, I'm going to let u equal 1 over x, because 1 over x is inside of another function. Now, when I look at the whole thing, you're saying, why didn't I choose x squared? Well, I didn't choose x squared because x squared is not inside of another function. Well, I mean, I guess you could say, well, it's inside this rational function of top to bottom, but it's not a whole piece. I'm not taking a whole thing out of that entire function. Does that make sense? So what I'm doing here is I'm actually simplifying this. I'm taking this from cosine with another rational function inside of it, just a cosine of u. So that's a lot simpler. If I let u equal x squared, I still have a rational function. I haven't reduced it into any other form. So I'm picking something that reduces it to a degree. Now my du here, remember this is x to the negative 1, right? So when I do that derivative, that gives me x to the negative 2, right? With a negative out in front, and then dx. Now, some of you are looking at that and thinking, well, that's not really useful. Do I have that anywhere? Well, like over here, I have x to the 2. This is x to the negative 2. I'm going to do two things. First thing, I'm going to move this negative over here with the du, so it's going to be negative du equals, and then I'm going to switch this and make this x to the second power, 1 over x to the second power, and then the dx stays on the outside of that rational function right there that we just wrote, or the expression rather. Now it does match, and you're thinking, well, if I rewrite this for a second, I'm going to rewrite this as cosine of 1 over x dx times 1 over x squared, and then the dx right there, right? Now, once again, I have that piece right there. There's that piece, right? Those two match. And then up here, I had that matches that. So they do match now. So now I can replace them. So now I can switch my variables. So now I'm doing cosine of u. This whole thing is the du that goes on the outside of that, and of course it had to be negative. Now I can put the negative right here, or I can put it outside of the integration sign. It doesn't matter. I can put it in either spot. Okay, and if I put it outside the integration, that might make it a little bit easier to look at, although putting it inside, in my opinion, would probably have a similar effect. But integration of cosine, you kind of have to think backwards with these trig functions of, like, when I did the derivative of sine, I got cosine, so the integration of cosine would be sine. So this is negative sine of u plus c. Remember, u is equal to 1 over x, so I got to switch back to my original variable. So it's negative sine of 1 over x quantity plus c. And by the way, you can use any variable you want. Standard notation right here is c for that constant that we're adding on here, because this could have originally been negative sine of 1 over x plus 5 or plus 7 or plus 12 or something else, just plus some value there. And that's what we end up with. So there is our integration by substitution. 3 good examples, 2 involving trig, and if you notice, two of them involved rational functions as well. That's a pretty common one to deal with. So what you're looking for, once again, when we recap this just a little bit, you're looking for when you have one function inside of another function, and if you can do a substitution, you can get rid of one of those functions that is embedded inside of another one. All right, enjoy and keep mathing on, okay? Take care.